So good afternoon, everyone. Welcome to Math 115 study sesh. So what I did in class this morning was basically to go over all of the different topics and just kind of introduce them all and give you a reminder about what is the content that is going to be on the exam. So what I'm hoping to do during this session is a bunch of practice problems. So what I'm hoping is that some of you have started studying and have come across some, not shaming anyone, but I'm hoping that some people have some questions from the homework where they were like, I was going back over this homework and I couldn't remember how to do this problem, can you help? So think on that for a second while we quickly do two example problems just to warm up here, where we want to convert, okay, between degrees and radian measure. Okay, so it's helpful to have an idea beforehand of just kind of like what generally do angles look like in degrees and radians, and that way you can kind of check yourself and see whether like you have a reasonable answer in the end, okay? So having a good grasp of like how many radians does it take to go halfway around, quarter of the way around, all the way around, etc. will be helpful for that. But let's just start with the first one, okay? So we start with a degree measure and we want to go to radians. What should I do? Multiply by pi over 180. How can I remember whether I'm supposed to do pi over 180 or 180 over pi? Yeah.
When you go to radians, pi's on the top. So when you want pi to stay on the top.
Yeah. When we go to radians, we want pi to be on the top. And in general, what is this number? This number is like 3 point something divided by 180. This number is much less than 1, right? It's like a fraction, like 3 over 180, right? So it makes sense when we go to radians, a big number like 135 is going to turn into a much smaller number in terms of radians, because 1 radian is like 59 degrees or something like that. Okay, so we multiply by pi over 180, and now we just simplify, okay? We simplify. So this is 45 times, you can rewrite this as 45 times 4, and you can rewrite this as 45 times 3, and cancel the 45s, and we get 3 pi over 4. Any questions on that? Okay, so multiply by pi over 180. What do I do when I want to go from radians to degrees? I'm going to take my radian measure and I'm going to multiply by 180 over pi. The way you can remember this one is, look, you want the pi's to cancel, right? That's what you want. So the pi needs to be in the denominator in order for that to happen. So 3 goes into 180 60 times.
I just bought a new one.
Is your bottle?
Yeah, it is.
Go for it.
30 weeks ago. I really bought a new one yesterday.
All right. I thought you were having an excited outburst about converting about converting here. Okay. Anyway, so cancel, and what's 5 times 60 is like 300, right? 300 degrees, okay? And check, look, this should make sense, because think about it. 5 pi over 3 is almost 6 pi over 3. 6 pi over 3 would be 2 pi, which would be all the way around the unit circle, but we're going to go pi over 3 less than that, which pi over 3 is 60, so we're going to go 60 degrees less than all the way around the circle. That's another way you could think about it. Okay, so this is how we convert. I think that's all I want to say about that. So with that, let's jump into student questions. Anyone have a homework problem that they want to talk about? Yeah.
Can I do a quiz problem?
Which quiz problem?
Just past one, quiz 6.
Okay, what is it?
Pythagorean identities.
Okay. So the question was sine squared of pi over 8 plus cosine squared of pi over 8 plus cotangent squared of pi over 3? Okay. So the first thing that we can recognize about this is, look, we have a lot of square terms, okay? And also the problem directions mention the Pythagorean identities, okay? So probably we're going to try to use those. Another hint that we should use those if the directions didn't say so is also to look at what is the input. The input is pi over 8. How are you going to do sine of pi over 8 and then square it? You can't even figure out what this number is. The reason you can't figure out, should be one chair left maybe, or two. The reason you can't figure out what this is, look, what does pi over 8 look like? It's like a 22-degree angle or something like that, okay? We don't have any rules for finding like the side lengths of a triangle with an angle in here of pi over 8. We could do it if it was pi over 4 or pi over 3 or pi over 6, right? But we can't do it for pi over 8. So we're kind of hosed if we want to try to just evaluate this. But what we need to remember is, maybe I'll keep that actually. What we need to remember is the following. This point has coordinates. The x-coordinate is cosine of pi over 8, and the y-coordinate is sine of pi over 8. So, sine of pi over 8 is this length, cosine of pi over 8 is this length. If I square those lengths and add them together, what am I going to get? 1. I'm going to get the length of the last side squared. So this piece here is nothing but 1. So we can rewrite this whole expression as 1 plus cotangent squared of pi over 3. In a hurry. Okay, so now what can I do? I can use another Pythagorean identity, or I could just try to evaluate this, because this is something I can do. The angle inside here is something I can handle. So I could do this one of two ways. The first way would be to do a unit circle, and I'm going to put inside of my unit circle the angle pi over 3, aka 60 degrees. And I'm going to look at the coordinates of this point, which by now, probably we can find them pretty quick. This is a 60, this is a 30, this is 1. That means this one's 1/2, and this one's square root 3 over 2. So the coordinates of this point are 1/2, comma, square root 3 over 2. So if you want, you can go ahead and just do the following. You can say, okay, I'm going to do cotangent squared of this thing. Cotangent is going to be x over y, right? Okay, so we take, actually it's going to, cotangent squared is going to be x over y quantity squared. So this would be 1 plus, and now I'm going to do x, which is 1/2, divided by the square root of 3 over 2, all squared, which would be 1 plus, okay, I'll go slowly so that we see what happens here. Divide by a fraction, same as multiplying by reciprocal. 1/2 times 2 over the square root of 3, all squared. Cancel the 2's. 1 plus 1 over the square root of 3 squared. What's this number? It's just 1/3. You could rewrite it if you really want as 1 over the square root of 3 times 1 over the square root of 3. Multiply the numerators, you get 1. Multiply the denominators, you get 3. So this, all told, is 4/3. That's method 1. Method 2, I'll show you in pink, would be to say, screw this. This is a Pythagorean identity. I know that 1 plus cotangent squared of pi over 3 is equal to cosecant squared of pi over 3. So cosecant would be 1 over sine squared of pi over 3, which would be 1 over, whatever the y-coordinate is, square it. 1 over the square root of 3 over 2 quantity squared is going to be 1 divided by 3/4, which would be 4/3. So two different ways of doing that. Any questions on this one? So what was the cue to use a Pythagorean identity?
Set it in.
Other than it said it in the question. Yeah?
It was two, like they have the same input and they were both squared.
Yeah, they're both squared and they have the same input. That's a big cue. Another cue is, look, without a Pythagorean identity, how the hell are you going to do something like this? You don't have any tools to do that unless you had a calculator, but you're not going to have a calculator on the exam. Okay, so recognizing these square terms often go along with these Pythagorean identities. Okay, any questions on that one? Another example of Pythagorean identities? Sure. Yeah, okay, let's do. I mean, I'm not really sure what else I could do other than, like, we could see one of the other ones. How about, like, tangent squared of pi over 6 minus secant squared of pi over 6. Evaluate. Okay, evaluate. So if we just want to find this, it's a situation where you probably could just go ahead and do it, but it's going to take a while and be a little bit annoying, and you can save yourself some time by knowing that tangent squared theta and secant squared theta are involved in one of the trigonometric identities, and let's say that I don't remember exactly what it is. I don't remember what that trigonometric identity is that has tan squared and secant squared, but I do remember the one that I always must remember, which is that sine squared theta plus cosine squared theta is equal to 1. I remember that one, but I don't remember the one involving tangent and secant. So what do? Well, I can take this identity and do the following. I'm going to divide by either sine squared theta or cosine squared theta in order to get what I want. What I want to have is a tan squared theta in my final result. So I'm going to divide everything by cosine squared theta, because if I divide this by cosine squared theta, then this whole term will turn into tan squared theta. So I'm going to take this whole equation and I'm going to divide both sides by cosine squared of theta. So I get sine squared theta over cosine squared theta plus 1 is equal to 1 over cosine squared theta. In other words, tangent squared theta plus 1 is equal to secant squared of theta, yes? So what do I have? I'm supposed to find out what is tan squared of something minus secant squared of the same thing. Can I use this identity to help me figure out what it is? How can I do that? Yep.
Make it look like it's going to take the second part of their side and then subtract 1.
Exactly. This is almost the same thing as the left-hand side. If I were to move the 1 over and move the secant squared over, then it would look just like that. So let's do that. So another way to rephrase this identity would be tan squared theta minus secant squared theta is equal to negative 1. So what is this? It's nothing but negative 1. Okay, so those are the Pythagorean identities. There's one for sine squared plus cosine squared. There's one for tangent squared and secant squared. And there's one for cosecant squared and cotangent squared. Which, if I wanted that other one, rather than dividing this whole thing by cosine squared, I would divide instead by sine squared. All right, how do you feel about that, Emma?
Good.
Should we move on to a different topic?
Mm-hmm.
Okay. Who's got another topic for me? Or another question from the homework? Yeah.
Could you do a half-life problem?
A half-life problem, sure thing. Do you have one pulled up? No? Okay, let's see if I can find it. That was in, what section was that in?
3B, I think.
Yeah, it was B. Well, do we need to know that?
Hmm?
Do we need to know that?
calculators used for half-life?
Sorry?
Don't you have calculator?
No, you could express your answer in terms of logarithms.
Oh, okay.
They're there.
Half-life. These are all doubling time. Here we go. All right. This is a good one. So determine half-life. I'm gonna show you the screen in a second. I just gotta write it down first. Huh?
What are the odds one of these are on?
You know I'm never gonna answer that question.
There's something wrong. Could you like not answer it, but like secretly answer it? Like,
That sounds like just answering it with extra steps.
Yeah, yeah, exactly. Like, what are the odds that will build test?
Here's what I would say. I would say that, look, all of the material, okay, is just applications of the same handful of skills. So regardless of what shows up on the exam, if you understand the skills, you'll be able to attack the problem. Doing this problem is going to teach you valuable skills whether or not the problem itself is on the exam. Deal? That's not what you want, but it's not what you want, but that's what I can say. Okay, so did I write it down right? I think I did. Okay. So, what does it say? It says determine the half-life given that we started with 43 kgs of a substance and after 15 years I had 24 kgs left. Okay, so what is the equation that we use for half-life problems? The equation for, we'll start with A of t is equal to what?
A of 0.
A sub 0.
Times e to the power of kt.
Good. Times kt. Okay, so what do we not know? We do not know k, and we know all of the other things. So let's put all of this information into this equation. What will my new equation look like? Someone tell me.
43 times 15.
43 times 15?
24 equals 43 EK.
Yeah, 24 is the end result, is equal to what I get when I plug 15 and A naught into this equation, which would be 43 times e to the 15k. Yes? Okay, so here's what I mean by crucial skills will be learned here. What do I need to do now? Well, yes, but more broadly speaking, I need to solve for k. The thing I want to solve for is in the exponent. What is the tool that we learned that gets things out of exponents? Logarithms, right? So the first thing to do, as Lauren said, is to get rid of this 43, okay? We're going to divide on both sides by 43, okay? The reason is I want this e to the 15k to be isolated so that I can do a log. So on one side I have e to the 15k, and on the other side I'm just going to write it generally as 24 over 43. Just going to leave it as an improper fraction, or actually it's a proper fraction. Okay, so now I need to figure out what k is. What is the next step? I've gotten this thing isolated. What should I do now? Well, it's not exactly that we're going to add ln so much as these two numbers are the same, right? So what I'm going to do is actually I'm going to use them both as the input in the ln function. Okay, so if by add you mean write, then yes, we're going to write e to the 15 ln, but it's not an addition process, it's a plugging process. We've plugged this number in to the ln function, right? And if I plug the number on this side into the ln function, I'll get the same number if I plug this number into the ln function, because the numbers are the same. So the output of the function will be the same. So this becomes ln of 24 over 43, yes? And now what can I do? What happens on the left-hand side? Like so? Okay. Only there's a easy simplification that we can do now. What is this number? 1. This is 1. Also, you can just view these as I'm taking 15k and I'm doing two things. First, I'm taking it to the e power, or taking e to that power, and then second of all, I'm doing the natural log. These two processes undo one another. So if I start with 15k, do something to it, and then undo it, what will I have left? Just 15k. Okay? You happy? All right, so now I get k by just dividing both sides by 15. So ln of 24 over 34.
43.
Whoa, sorry, thanks. Miscopy. 43, and then divide all of that by 15. Okay, great. Now I figured out what k is. Am I done? Would you say it's this many years? That's the half-life? No. What did I actually determine?
Okay.
I determined what k is, which k is not the half-life. K is the decay rate. Okay? So how am I going to then use k, which I've just determined is this number? So what did I do? I basically did all of this to add an extra piece of information to my puzzle, right? Add an extra piece of information. So now how am I going to determine the half-life given this k value? Sorry? Plug. Okay, so can you tell me exactly what you had in mind in terms of what I should write?
Is it L divided by k?
Okay, yeah, you can do that. But let's do it from scratch. But yes. But I doubt that many people in this room have that fact memorized. I certainly don't. So let's see how we do it. With this newfound information, okay, I can give the exact formula of what is A after t years. So A of t is equal to what? A naught is 43, yes? Times e to the ln of 24 over 30 over 43 over 15 times t. Okay, I just replace k by k, replace a naught by a naught. How is this going to help me figure out what the half-life is? Well, if I plug 15 in here, what am I going to get? I'm going to do 43 times this stuff after I multiply it all out. What am I going to get? I'm going to get 24, which tells us that, look, if you start with 43 kilograms, after 15 years, you're going to have 24 kilograms left. But 24 is not half of 43, is it? So how should I proceed? Maybe we can phrase the question. I'm looking for the half-life, which is a measurement of what?
Time.
Yeah, it's time, right? It's a measurement of time. So I want to find t, the time, such that if I plug it in here, what happens? I want to find the amount of time that it takes for what to happen?
It to decrease?
For it to decrease to half of its original mass. Does that make sense? So what I want to know is, look, I'm going to wait for a certain amount of time. If I start with 43 kilograms, and at some later time I have half as many kilograms, how many kilograms will I have? Yeah, I'm going to have, I want 21.5 to be the output of this function. And my goal is to find the input t, which makes that to be true. So this would be equal to 43 e to the ln of 24 over 43 over 15 times t. Now I must find t. Okay? Now I must find t. How am I going to do that? Yeah, but broadly speaking, the thing I want is where? It is in the exponent. What is the tool that we use when the thing that we want to get by itself is in the exponent? Natural log. But I can't apply natural log right away, can I? Because I have this pesky 43. Okay? This is what I want you to think about as you're doing this type of problem, is say, look, okay, the thing I want is in the exponent, so I know I need to use a natural log. And then you say, but I can't just go ahead and use a natural log because this 43 is here. So that leads you immediately to what you need to do, which is divide both sides by 43. If you ask yourself these questions of like, what am I really trying to do? How do I accomplish that? What's preventing me from doing that? These will lead you to the correct steps that you will need to do. Okay, so we divide by 43 on both sides, and we get what? 1/2 on this side. And then on the other side, we get ln of 24 over 43. Now, what am I doing? We still have e in here. We have e to this number times t. Now I can apply the natural log. So I'm going to do that on both sides. And we get ln of 1/2 is equal to, not e, the ln and the e cancel one another, and we're left with just whatever was in the exponent, which was ln of 24 over 30. Jeez, 43. I don't know why I keep writing 34. And also I missed a 15. Over 15 times t. So what is t going to be equal to? T will then be equal to, it's being multiplied by a fraction, multiply both sides by the reciprocal of that fraction, and I'll be done, right? So t is going to be ln of 1/2 divided by ln of 24 over 43 times 15. Or you could put the 15 up here if you want. Okay? So totally reasonable. I didn't need to use a calculator for any of that. So yes, this is fair game for the exam. What you need to know, okay, is broadly speaking, these tools of how do I isolate what I want when it's in the exponent, right? How do I isolate what I want when it's in the exponent? And then also, how do I infer this equation? This equation, we said, well, look, I want to find the amount of time t that it takes for me to have half of what I started with. If what I started with was 43, I should have 21.5 at the end. And then I just use the formula, I fill in all the pieces of information which I know, and I solve for the one piece which I don't know. Yeah?
Doesn't matter where you keep the 15, the numerator or the denominator.
Well, if you wrote a 15 here, it would be a different number, right?
Well, I mean like over 15.
Oh, you mean like so?
Yeah. Like.
I guess that's fine. It's not proper, but whatever. As long as you have t by itself.
Can you go over from how you got from like the ln 1/2, like the one on top to the bottom?
How I went from here to here?
Yeah.
Okay, so right now the thing that I want is being multiplied by a fraction.
Right.
The way I'm going to cancel that is by multiplying both sides on the top by, multiplying both sides on the top by 15, and then multiply the bottom by ln of 24 over 43.
Okay.
If I do that, then this one's going to cancel with this one, and this one's going to cancel with this one. Why don't I do it sideways? This one's going to cancel with that one. And then on the left side, I have to do the same thing by multiplying the top by 15 and multiplying the bottom by ln of 24 over 43. Oh, that's okay. Sometimes I go kind of fast, so if I ever go too fast, just ask me to go back, all right? Any questions? Any further questions on this one? I kind of wish I brought some water.
23 weeks old.
No, that's okay. I'm really all right. All right. Any more questions on this, or should we move on to a new topic? All right, that sounds like new topic to me. What's the next topic?
Stretching vertically and horizontally for graphs of sine and cosine.
Absolutely. So, stretching and compressing sine and cosine. So let me go back to the notes, actually, and I'm going to copy in the relevant section. So that's 4.45, I think. Okay, why don't I just paste it down here? I'll move this down. Okay, stretching and compressing sine and cosine. So let's review. Well, we know that any function that we multiply by a number on the outside is going to experience a vertical stretch or a vertical shrink. It's going to depend on whether that number is bigger than 1 or smaller than 1, right? And then also, if it's negative, then we'll also have a reflection, right? We could have a reflection too. Okay, so in order to make the graph of a sine x, all we're going to do is we're going to multiply the height of every point on the sine function by whatever a is. So in this example, we had a was equal to 3. So I take the normal height at 0 is just 0, because sine of 0 is 0, so it stays at 0. But at pi over 2, the height of the sine function is 1. So the height of 3 times the sine function will be not 1, but 3. Okay? So that's how we stretch vertically. If we were going to shrink vertically, well, it would be like a 1/2 here, right? A 1/2 would cause us to have a vertical shrink. And then, where would I go? Instead of going up to 1, I would go up to just a half, right? To right here, and then like so. And it's still going to pass through the x-axis at the same points because 0 times anything is 0. And if it was like -1, then it would look like this, okay? Because of the reflection, right? Any questions on stretching vertically so far? We're going to see an example in a minute here, but is the concept feeling okay? All right, thank you for actually verbalizing that for me. Okay, let's talk about horizontal stretching. Well, we know we're going to have a horizontal stretch or shrink depending on whether or not we have a number being multiplied on the inside. A number being multiplied on the inside. Okay, so the tricky thing about horizontal stretching is that we're going to have a horizontal stretch when a is less than 1, because we're living inside of the parentheses, right? When we're inside of the parentheses, we got to remember everything is like the opposite of what we think it would normally do. We think big number makes it bigger, but actually when we're on the inside, we're in the, we're in opposite world. Big numbers are going to cause our graph to shrink in the horizontal direction. And likewise, small numbers, which are less than 1, are going to give us horizontal stretches. Okay, horizontal stretches. So let's see an example. Let's try to do the graph of I don't know, 2, no, why don't we do negative 2 cosine of 2x? Okay, negative 2 times cosine of 2x. One thing that I feel like is helpful is probably start by graphing the parent function. What does cosine look like originally so that we can, you know, have an idea of what the transformation is going to look like. And let's do this on the interval from 0 to 2 pi. Well, normally, cosine of x would look like what? What is cosine of 0? It's 1. Okay, the way I know that is because, look, draw a unit circle, 0-degree angle, points straight to the right. The coordinates of this point are 1, 0. Since we're doing cosine, we're interested in the x-coordinate. And then what's going to happen? So we start at 1, and then we're going to work our way around the unit circle like so. So think about what's going to happen to the x values as we work our way around this circle. The x value starts at 1, and then the x value becomes closer and closer to 0. And then the x value becomes closer and closer to -1. And then the x value becomes closer and closer to 0 again. Remember, we're talking about the widths of all of these, right? So it comes closer to 0 again, and then it's going to go up, 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 up to 1. So that means that the graph of this thing is going to look like so. Here's pi over 2. Here's pi. Here's 3 pi over 2. And here's 2 pi. Cosine is going to look like the following. As the angle measurement goes from 0 up to pi over 2, the value of cosine is going to go from 1 down to 0. So we go down, 1 down to 0, yes? And then what's going to happen? As the angle goes from pi over 2 up to pi, the x value of points along this trajectory, the x values are getting closer and closer to -1. So we get closer and closer to -1, and that's where we bottom out. And then we go up again to 3 pi over 2, and then up like so. And if we were going to repeat this graph, we would just keep going, right? Just copy paste. But we're only supposed to graph up to 2 pi. Okay, so now let's look at what we have here. We have what? This 2 on the inside is going to be applied first. And what is the result of multiplying by 2 on the inside for the graph of the function? Well, it's on the inside. So are we dealing with up and down world, or are we dealing with left and right world? We're on left and right world, okay? So it's going to have something to do with the horizontal direction, and it's going to be either a shrink or a stretch, depending on whether this number is bigger or smaller than 1. If the number's bigger than 1, that, to me, makes me think all the numbers are bigger, right? It should be a stretch. But remember, we're not on the outside, we're in the opposite world. And everything is the opposite of what we think it should be. So what is a 2 on the inside going to do? It's going to give us a horizontal shrink or compression by a factor of 2. Okay? Thanks. Okay, and how about this number 2? Actually, it's a -2. So let's start with just the 2. What's that going to do? Vertical stretch. So it's going to go twice as high. And what about this negative sign? Yeah, reflect. Okay, so if I have a horizontal shrink by a factor of 2, then what's going to happen is basically we're going to do everything twice as fast. So it's going to look something like this. This would be like just a horizontal shrink by a factor of 2, right? It's going to go twice as fast. And also I need to do the other 2 things, which is namely a vertical stretch and a reflection. So vertical stretch would take us from here to looking more like this. And then reflection is going to reflect us about the x-axis. So what's going to happen is, look, this point is where the input is 0. If the input is 0, the inside is 0. Cosine of 0 is 1. Multiply that by -2 to say, okay, the height of this point is 1. The new height of our new graph should be -2. So what is the graph of this guy going to look like? I'll do in blue. We start at -2. And we should complete basically this kind of a picture in half as much time, right? If it was just reflected, it would look something like this, right? But we need to have the horizontal shrink by a factor of 2. So it's going to get shrunk and do this not in 2 pi units, but it's going to do the whole cycle in just pi units. So it's going to look something like this. No, not like that, sorry. It's going to look something like this. And as we get up to here, it's going to max out at a height of 2. Okay, it's going to max out at a height of 2. And then it's going to come down, and it's going to go through here, and then it's going to get down to its minimum height again. And now we've finished one cycle. So if I'm supposed to graph it on the interval from 0 to 2 pi, I still need to do the graph of it right here. How am I going to figure out what the graph of it looks there? I'm just going to repeat the exact same thing. Okay? So again, it's going to do the exact same thing. Whoops. Goes up, hits that maximum again, and it's going to come down. And then it's going to go down to the minimum one more time. Okay. Any questions on that? Yeah.
I don't have any examples of this in the homework, but like I know it is there. On a few of the questions, it didn't have the height being at the exact same points, like -2 versus 2 kind of thing. Having those points, it was like -4 and like 2 for some reason.
Mm-hmm. Okay. Let's see if we can take a look at a graph and determine what is the function. Let's say I give you the following graph. Okay, I give you the following graph, which I gotta modify my axes a little bit here. Let's go all the way up to 3, like you said. Let's say I gave you this picture. And it should hit a... It should return to 1 at pi, and then it's going to dive down. And then at 3 pi over 2, it should hit the minimum. And then it should go up to 1 again. Okay. So something like this, is this what you meant?
Yeah.
Okay. So something like this, and let's say, okay, is this y equals a sine of bx plus c, or is it y equals a cosine of bx plus c? Something like that, what you had in mind?
Yes.
Okay, so we're supposed to figure out what are a, b, and c here. So the first thing to recognize is the following. Let's just say, before we start, what kind of transformations are we going to get out of these? Okay, we have what transformations? There's 3 of them. Can you list them in order? What are the transformations on this function here?
Movement of the horizontal.
We have a horizontal what?
Shift.
Stretch or shrink. Stretch or shrink. And we have a vertical stretch or shrink. And we have a vertical shift. Okay? But I claim you can immediately throw one of them out. I'm telling you that there is not one of these transformations. Which one can we immediately rule out?
Horizontal.
Sorry?
Horizontal.
Yeah, I can immediately rule out, I know I don't have a horizontal stretch or shift. Why?
Because it's not the period of projected over.
Yeah, what's the period of this graph? It repeats on the order of 2 pi. Sinusoidal graphs, like sine and cosine, are 2 pi periodic. The period is unchanged, so I can say, without a doubt, I have no horizontal stretch. In other words, B is just 1. Okay, B is just the number 1. Because I have no horizontal stretch. Is that clear, or should I go through that one more time?
Can you go over that one more time?
Yeah, one more time. Okay, so I'm trying to identify which of these graphs it could be. My goal is to figure out what are the numbers A, B, and C, and also should I use sine or cosine, but we'll get to that in a second. The first thing I recognize is, look, this graph completes a full cycle after 2 pi units. The period of sine and cosine, i.e. the amount of x values which it takes for it to start repeating, is 2 pi. So if I were to have a horizontal compression or a stretch, I would expect the period to change, right? Because if I were to say, do something like this, yeah? If I were to do something like this, this would seem like, oh, it's repeating after pi units, right? It's repeating after pi units. So it's like going twice as frequently, right? But this is just going the normal frequency, so I'm happy to say there's no horizontal stretch or compression. Feeling better now?
Yeah.
Okay, let's move on to the vertical stretch and the vertical shrink and the vertical shift. So one thing I notice is, look, my maximum height is 3, but my minimum height is -1. Okay, what does that tell us about our transformations?
That the amplitude is 2.
Yeah, it tells us that the amplitude is 2, namely the distance from peak to valley is 4. Half of that is 2, so our amplitude is 2 because the amplitude is the measurement from basically where we have it's like we have an imaginary axis here, right? Okay, so not only does that tell us that we have a vertical stretch, but also that we have a vertical shift, right? The reason I can tell that there's a vertical shift is, look, normally these graphs are symmetric in the sense that the peak is at like a positive x value or positive y value, and the valley would be at the negative of that same y value. Okay, but I don't see that here. I see a wonkiness. So it's like this whole thing has been picked up and moved upwards, right? Whole thing has been picked up and moved upwards in addition to being stretched. So normal amplitude is just 1 for sine and cosine. My observed amplitude is 2. Okay? So what is the difference between these two? I get 2 by multiplying 1 with 2. So this tells me that A is equal to 2. A is equal to 2. Okay? So now I know A and B. The final thing I have to figure out is, what is C? Right? What is the vertical shift? Well, I don't know what you want to call this, but I don't know, like the baseline, basically, of our graph here has clearly been shifted up 1 unit, because a sinusoidal curve with amplitude 2 should go from -2 up to 2. But ours goes from 1 to 3, which means we've just taken the whole thing and moved it up. How many units? Just 1 unit, okay? So this tells us that C should be equal to 1. So the question now that I know A, B, and C is this the graph of y equals 2 sine x plus 1, or is this the graph of y equals 2 cosine of x plus 1? We need to determine which one is the correct formula. How can I do that?
Looking at where the graph starts.
Yeah, looking at where the graph starts, or broadly speaking, the shape of the graph, right? This is the shape of which trig function? This is the shape of sine, right? If it were cosine, it would look a little different. It would look like this, right? That's what it would look like if it were cosine. Look like this kind of like U shape. Or if you want to continue it in the other direction, people say it looks like a bell shape. Okay, people say it looks like a bell. Okay, but this has to be sine and not cosine. And let's say that you don't know, you don't remember what they're supposed to look like. Here's what you can do. Just try plugging in. If I do 2 times sine of 0 plus 1, what do I get? Sine of 0 is 0. So this is 0. So this whole thing is 0. And I would get 1. So if this is the correct formula, then I should observe when I plug in 0, which is this x value, I should get 1, which I do see that that is true, right? Let's try it with the other one. I'm going to try plugging in 2 cosine of 0 plus 1. What would I get when I do this? 3. So if this is the correct formula, then when I plug in 0, I should get 3. But when I look at the graph, I do not observe that phenomenon. So I can rule that out. All right, any questions on this example? That's probably as hard as it could get with the transformations of sine and cosine. All right, how are we doing on time? Oh, plenty of time. Okay. New topic? Who's got one? Yep.
Are you gonna make this graph a log function? Well, I guess I can't answer that. I guess you can't answer that.
No, you can answer.
3.2, like number 15, 16.
Sure. Let's take a look at 3.2, number 15 and 16. Preview.
Quizzes that have
Mm-hmm.
that are on this exam, like with the same whatever.
Units.
Yeah. Or quiz 5 and 6, right? That's it. And then the rest of it is just
I really don't remember what quiz 4 was on.
Oh, you're a teacher.
Who would remember that?
So
that was
I
so
can
aggressive
check.
For no reason.
Let's see. Let's see what quiz.
That was on the quadratic, that was minimum and maximum, range of function.
This was quiz 4.
That was last unit.
Let me see that.
Yeah, that's.
Last unit.
That was when we had to
It's
memorize
okay.
all, well, you wanted us to
Wait,
memorize like.
What the hell? Oh
absolute
yeah, no,
value
that's fine.
functions and all
So
that.
then it's
That's
just
not
5
on the
and
quiz.
5
That's not
and
on the
6.
exam. Yeah, it's just 5 and 6.
And then the new
Six
stuff.
back.
I just gave it back actually in
But
this
in
like
here.
right now. Do you want yours? Who doesn't have their quiz 6 yet? Gavin, come get yours.
Alright.
And we got Alexa and Ian. And anyone else?
After this meeting, it's expanding.
Yeah, give me a sec. Jesse? Really? Mm-hmm. What am I doing? Looking for Funk, right? Funk. There you are. And Doyle, right? Yours is here. Anyone else need their quiz still? Okay. I don't like that problem. We're not going to have that problem on the exam.
Oh, we're not?
Which one?
This one.
Oh.
We're not going to have this one on the exam. And we're not going to have this problem either. Okay, what I'm not going to do is something like okay, let me just say now. I'm not going to put something like this on the exam or like this in terms of find the domain. Okay, I will not ask you a question like this. The reason is this is a sum of functions and a division of quotient of functions. We did not really talk, we did talk about, but we did not talk about in detail how to find the domain and range of a sum of functions or a quotient of functions. What I did focus on heavily was how to find the domain of a composition of functions. So this, no. Something like this is fair game for the exam, okay? Compositions of logarithms will be fair game. I will not do a domain and range of a quotient of two different logs or a sum of two different logs.
But that was on the quiz.
No, it wasn't. This one was on the quiz.
Yeah, that was on quiz hall.
Yeah. And we talked about it in class this morning, so I'm not going to go over it now. Okay, so with that in mind, should we do something else maybe?
I was talking about 15, 16.
Oh, whoops, okay. I thought you said 12 and 13 for some reason. Okay. Yeah, sure, let's do this one. Graph.
Let's go information first.
Graph log 1/4 of x. Okay, so log a of x always passes through which 2 points? Who can give me one of the points that a logarithm always passes through?
A1.
Yes. A1, and what's the other one?
1, 0.
1, 0, good. So in this case, A is 1/4, so this one's gonna pass through 1/4, comma 1, and 1, 0, right? And 1, 0. So let's see what this is gonna look like. So here's the point 1, 0. And 1/4, comma 1 is like here. This is 1, so this is 1/4, and this is 1. Okay, so we know we have these 2 points being passed through by this logarithm. Now, normally logarithms look something like this, don't they? What's up with this? We got a point up here for some reason. Why is that? Why is this point sort of out of place for a logarithm function?
Is it reflected about the line y equals x?
Yes, it has to do with the corresponding exponential equation. Let's see what it looks like. If this is equal to y, the corresponding exponential equation would be 1/4 to the power y is equal to x, right? If I were to graph this as a function, okay, If I were to graph a normal exponential function, it looks like this. So when we reflect it about the line y equals x, it looks like this, right? But here's the deal. 1/4 to the power x is not an exponential growth function, is it? It's an exponential decay function. So the parent function looks not like that, but like the parent function looks like, I'm gonna fuck this up. Something like this probably is what it will look like. So if we reflect that about the line y equals x, what am I doing? Is this correct? Yes. No. Oh, what have I done? Okay, let me think about this for a second. So if we were to reflect that about the line y equals x, then what would it look like? No, it should be... Oh, I know why this is wrong. This is wrong because I drew it in the wrong spot. Okay, so what would it look like? Let's draw the line, the curve, y equals 1/4 to the power x. It would pass through the points 0, 1, and 1 1/4. So it would look something like this. Yes. So then we draw in the line y equals x. Hello. Okay. We draw in the line y equals x. And what happens? This point gets mapped down here. And this point gets mapped to here. Okay, because we're going straight across the line y equals x. So this goes straight here, this goes straight here, and the rest of it is going to look like the following. This piece is going to get moved to be here, okay? So this piece, we're going to copy it and reflect it over to here, okay? Like so. So the graph of, I'm running out of colors. I'll do y equals log 1/4 of x. It's going to look like so. Okay, where this part is corresponded to the reflection of this part. Okay, it gets reflected across the line y equals x. So it's a little hard to draw, to be honest. But what I would look for is, look, you need to have the 2 points, 1/4 1 and 1 0 on your graph. That's non-negotiable. Beyond this, you need to know that if a is bigger than 1, the graph of a logarithm, loosely speaking, looks like this. If a is less than 1, which is the case here, the graph of the logarithm will look instead like this, okay? So these are the 2 types of behaviors which I want you to be able to capture here, okay? Are, if a is bigger than 1, it will look like this. If a is less than 1, it will look like this. And make sure that you're passing through the relevant points, okay? That would be a full points response for a problem like this. Any questions on this one? You're right, Gavin?
I'm very lost, I'm gonna be honest.
Okay. Does anybody else feel pretty lost? It's totally okay if you feel lost. It takes some practice getting to know these, okay? But we would hopefully, I feel like you would feel more confident knowing that the graph of like 2 to the x looks something like this, whereas the graph of 1/2 to the x would not look like this, but it would look like this, yeah? It's gonna decay like that. So if you can remember that, then you can remember that there will be differing behavior for the logarithmic function based on whether the log value, the base, is bigger than 1 or smaller than 1. You're going to observe a similar type of difference in the graphs. Okay, so what you need to memorize is 2 shapes and 4 numbers, basically. 2 shapes and 4 numbers. That's what you need to memorize. And you need to memorize also where the numbers go, obviously, which is that log a of x passes through 2 points always. It's the reverse of the 2 points that an exponential function always goes through. The exponential function a to the x always goes through the points 1a and 0, 1. That's where we get these 2 points. It's the flip. It's the flip of them, right? Okay. I mean, that's all I want to say about the graph of logarithmic functions. Any other questions from different section, maybe?
I just, never mind, I'll just last thing, sorry. I just saw this question, so it's pretty good.
Well, let's maybe look at that question that you asked in class this morning, which I said I was going to do in the afternoon. Where did I write that stuff?
I have the question, so if you want it.
Yeah, I just don't remember where I wrote it all. I was writing a bunch of stuff.
Skip it, actually.
Here it is. Okay, let's do this we're going to do 2 problems. The first problem will be one of these. We're going to do this, but then we're going to do this. And then we're going to do one which will be the opposite of that. So it will be tan inverse of tan of, and I'm going to do 7 pi over 4. Let's start with the first one. Okay, let's start with the first one. What I want to do with these problems, okay, is work from the inside to the outside, okay? And I want to be careful not to fall into a trap. Let me tell you about the trap. The trap is to say, well, this is like doing something, right? And this is just undoing that thing, right? So, bam, done, square root 3. This is a trap because when we're working with inverse trig, we have very specific outputs in mind for the inverse function. In the case of this example, this one actually will be the square root of 3. We'll see it through, and it will be the square root of 3. But this one is not going to be 7 pi over 4 because of that issue with the trig functions, which is they're not one-to-one. So when we do the inverse, we have to restrict our vision to a subset of the circle. Okay? So let's see how this works. I'm going to go through, again, this problem, just from scratch, do the inside part first. So what am I looking for? Tan inverse means I'm going to work on the right half of the unit circle. Okay, I'm going to work on the right half of the unit circle. And what I'm looking for is a point on the right half of the unit circle such that the ratio y over x of the point on the unit circle is equal to the square root of 3. So what does that tell me? That tells me that y is equal to square root of 3 times x. So I have a triangle in here. I know I have a triangle. And what have I learned? I know that the height of the triangle, namely this length, is square root of 3 times the width. There's only one type of triangle whose side lengths obey this type of relationship, and that is if this length is 1/2 and this length is square root of 3 over 2. And this one is 1. If you want to see why that should be true, you could easily plug this into the Pythagorean theorem. You get x squared plus what is y? Y is the square root of 3 times x, so I'm going to do square root of 3 times x squared is equal to 1 squared by the Pythagorean theorem. Therefore, this simplifies to 4x squared equals 1, so x squared equals 1/2, no, equals 1/4, getting ahead of myself, and therefore x is equal to the square root of 1/4, which is 1/2. That's one way you could figure out what this length is if you didn't immediately recognize that this is going to be a 30, 60, 90. Okay, so just reviewing what we did in class this morning, we then determined the angles, the interior angles. the side which is across from the smallest side, or sorry, the angle which is across from the smallest side will be the smallest angle, which means it must be the 30, and means this must be the 60. So what then is the output of tan inverse of the square root of 3 is equal to? What do we get as an output? Well, let me ask a simpler question then. The tan inverse function's job, okay, all functions' job, is to take something as an input and then give you back something as an output. In this case, the input is the ratio of the y-coordinate to the x-coordinate of this point on the unit circle. And what should tangent inverse give back to us? Yeah, an angle. Okay, probably a lot of you were thinking that. I hope a lot of you were thinking that. Because tangent, or all the trig functions, what do? They take an angle, give us something to do with the coordinates. The inverse trig functions will take the coordinates and give us something to do with the angle, right? So I need to give the angle such that if I put it inside the unit circle, it points at a point whose y-coordinate divided by the x-coordinate gives us this number. And what is that angle? Pi over 3. Good. So this should be pi over 3, yes? So I figured out what that internal thing was. Now my goal is just to do the following. Now I just want to do tan of pi over 3, right? That's all I want to do. I figured out what tan inverse of that thing was. Now I'm plugging whatever is the answer from that into the tangent function. So let's do this one. It's going to look identical. Okay, you'll see. It will look identical. What is pi over 3? It's a 60-degree angle, so I'm going to put it in. Here comes my 60-degree angle. And I know the coordinates of this point are 1/2, comma, square root of 3 over 2. Okay, you can figure that out if you want using 30, 60, 90 triangles. I know this one is a 60, I know this one is a 30, and I know this length is 1. So I determine that this one, this side length should be 1/2, this side length should be square root of 3 over 2. So what is tangent's job? It takes an angle and gives us back what? Yeah.
Y of x.
Yeah, where y is the y-coordinate of the point here, and x is the x-coordinate of this point here. So what do I get? Square root of 3 over 2 divided by 1/2, which is the same as square root of 3 over 2 times what fraction? 2 over 1. We reciprocal, right? So it's reciprocal, and I get, as a result, square root of 3. Okay, so what did we learn? We said, look, tan inverse of square root of 3 gives us the angle pi over 3, and then I plug that angle back into the tangent function. So this is kind of like a we're doing something and then we're undoing that something, right? But we have to be really, really careful, okay? We have to be really, really careful because the tangent inverse function is going to give us a very specific angle, isn't it? It's not just that tangent of this point is the square root of 3. It's also the point whose tangent value is square root of 3, and that point lives on the right half of the unit circle. Because guess what? There is another function, or not another function, there is another point on the unit circle whose tangent value is square root of 3. That is this point here, whose coordinates are negative 1/2, comma, negative square root of 3 over 2. This point has the same tangent value, because tangent is pi periodic, if you want to think about it that way. Add pi to any angle, you'll get an angle such that the tangent value will be the same again. Okay, so tangent inverse's job is to give us the angle which is on the right half of the unit circle, which points at one of these points such that the ratio of the y value to the x value is square root of 3. Okay, so it's not just a foregone conclusion that you can say, well, these just, cancel, and we get square root of 3. Okay, we need to know how to do tangent and tangent inverse and sine inverse, cosine inverse. Okay, let's see another example. Okay, any questions on how we did this one, first and foremost? All right, then let's see the bad example. By bad, I mean the one where things aren't going to work out as we might expect. We might expect that, look, I'm doing something, and then I'm just going to undo what I just did. Shouldn't I get back 7 pi over 4? Enthusiastic no from Chris. Can you explain why?
It's not going to be 7 pi over 4. I know that.
It's not going to be 7 pi over 4. That's true. Yeah.
Wait, never mind. Oh,
Okay, never mind. Sully, you want to give it a shot?
It has to be in between negative pi over 2 and pi over 2.
Yes.
She has 7 pi over 4, which will be pi over 4, right?
We're getting a little ahead of ourselves.
Oh, wait, yeah, I know.
But the point is, look, no matter what I plug into the tangent inverse function, the output will be a number which is between negative pi over 2 and pi over 2, as Sully said. This number is outside of the range of the function. So it is not going to be possible as an output for this operation. Okay, so let's see what happens instead. Generally speaking, okay, Chris, you're right that it's going to be like some other kind of reference angle, which is similar to 7 pi over 4. It's going to be like pi over 4 or maybe negative pi over 4. That's what we think is going to happen. Okay, so let's see how it actually works. Okay, here we go. 7 pi over 4. What quadrant does this angle point in? It's in the 4th quadrant. Because 8 pi over 4 would be all the way around, right? This would be 8 pi over 4. 8 pi over 4. Since I'm doing 7 pi over 4, I'm going to do pi over 4 less than that. So it's going to be like a 45-degree angle in this direction, right? So this is pi over 4 here. Okay? So the angle 7 pi over 4 looks like this. 7 pi over 4. It goes almost all the way around the unit circle. So, what is the tangent function's job? You give the tangent function an angle, and tangent function will give you back what? Y over x of this point. What are the coordinates of this point?
Square root 2 over 2 and negative square root 2 over 2.
Good. You can memorize that, or you can draw a triangle. Right? If you draw a triangle, this is a 45, 45, 90 triangle. You can figure out the side lengths in that way. So, this is the same as doing tan inverse of what number? What is tan of 7 pi over 4 in light of these coordinates?
1. Or negative 1.
Negative 1. So we need to do tan inverse of negative 1. Okay? So now I'm going to forget, okay, about all of what I have already done. I'm just going to forget about it. I'm just going to work on this problem. Okay? I'm just going to work on this problem. So what do I need to do? I need to find an angle. I need an angle such that two things are true. Tan of that angle is negative 1, and what's the other thing that needs to be true for tan inverse? Not only does the angle need to give us an tan output of negative 1, but we also need one other thing to be true about that angle.
That's being the negative pi over 2.
Yes.
And pi over 2, right?
Theta needs to be less than pi over 2 and larger than negative pi over 2. So, I'm restricting myself to the right half of the unit circle. What is the point on the right half of the unit circle such that the y value divided by the x value is negative 1? It's going to be the angle negative pi over 4, which is going to point at a point whose x-coordinate is square root 2 over 2 and whose y-coordinate is negative square root 2 over 2. That will be the corresponding point. And I need to find the angle such that it points at this point, and the angle measurement is between negative pi over 2 and pi over 2, which leaves us with just one angle as a possibility. That was the whole point of restricting ourselves to the right side of the unit circle, is we only want one possible answer. And that answer would be the angle negative pi over 4. Okay, so tangent of negative 1 is the number negative pi over 4. So, here's an example of where we can't necessarily just cancel, be done with our lives. Okay. One thing I'll say is, look, the only situation where I'm actually going to have this danger is going to be when I'm applying the tangent function first and then the tan inverse. If I do tan inverse first and then the tangent function, you actually will be able to cancel every single time. But I don't want you to just do that, okay? What I want you to do is remember the process of how you can justify this cancellation process. Namely, look, this is doing something. Just do the thing that it's asking you to do, and then get the answer and do the next thing to it, okay? This will get you the right answer every single time. Okay? So, just make sure that you avail yourself of that process. Any questions of the tan inverse or the tan inverse tan? Cool. All right. I just wanted to give people time, because sometimes you either need some time to formulate your question or you need some time to work up the courage to ask it. So I try to give enough time for people to do that. Okay, we have 8 minutes. Okay, we have 8 minutes. What else should we do? Okay, let's take a look at the homeworks here. See what else have we not really covered. Mm-hmm.
Do the expansion of a logarithm.
The what?
Expansion of a logarithm.
Expansion of a logarithm. Yes, absolutely. What? Okay, that's 3.3a, I think. Pick one from in here. All right. So this one says it's log 9 of x minus 1 to the 4th divided by x plus 1 to the 9th. Okay, let's try this one. Our goal is expand fully. Someone help me out with the first step. Mm-hmm.
We get a subtraction.
Yeah, so I have a quotient on the inside. Quotient on the inside can be turned into a difference on the outside. So I'm going to rewrite this first as log 9 of x minus 1 to the 4th power minus log 9 of x plus 1 to the 9th power. Now let me quiz you. We'll work on this one in a second. But I have a question for you all. True or false?
Are those both 9s?
Mm-hmm. The power on the inside is the same as the base. Do they cancel out or not?
I do not think so.
Okay, how could we fix this statement? By just changing the left-hand side.
Put the 9 on the outside of the other parentheses.
Put it here. Yeah, that'd be one way to do it. That's true. Yeah, that would be one way to do it. The other way that I was thinking of would be to say this. This would be x plus 1. Okay, so don't get tripped up by that. Okay, just because there's a matching number on the inside doesn't necessarily mean we can cancel. Okay, so let's keep expanding, because our goal is to fully expand this. I mean, I did already break it up. Can I just call it here? No, I can't call it here because I still have powers on the inside. Okay, no powers on the inside allowed. So how do I undo them? Yeah, the power comes out front. 4 log 9 of x minus 1 minus 9 log 9 of x plus 1. Okay, and then we just have one step left to do, which is, of course, if I have a subtraction on the inside, we can rewrite that as a division on the outside. So this would be log x divided by log 1, right? Or have I made a mistake? Should expand as much as possible, shouldn't we?
Just not multiply.
Yeah. This is not the same as this. When we have a division on the inside, we can write it as a subtraction on the outside. Okay? Namely, log of m over n is equal to log of m minus log of n. But it's not true that log of m minus n is equal to log of m over log of n, okay? This is not true. So no, we cannot do that. So we should leave it right here. Okay, we can't expand any more than that. Any questions on that one? So the only rule we didn't use here was, of course, if you have log of a product, m times n. How can I rewrite that one?
Log m plus log n.
Yeah, log m plus log n. Okay, we'll stop there for today. Good luck on your exam tomorrow. I know you're all going to do great.
You'll be sleeping in.
Did you just take those days off? Just you can?
Yeah, actually, to